Dear students, it is a second session in inner products. We know what is this one? Set of C of closed interval 0, 1. This is nothing but set of all real valued continuous functions from the interval 0, 1. This is equal to set of all functions from the interval 0, 1 to R, also continuous. And we have seen that this is a vector space. Clearly we know that this is a vector space over R. Now we are going to define an inner product over this vector space. Is a vector space. It's a vector space over the field R, right? If for f comma g in C of 0, 1 closed interval 0, 1, if we define inner product of f comma g as integral 0 to 1 f of t into g of t dt. Actually you may put some even some dash if you wish, but this notation is important for the inner product. To distinguish some different inner products, we may put some 1, 2, some dash, etc. If we define this inner product as this, like this, then show that this vector space together with this inner product is an inner product space. Show this one. So proof. What we have to show, first of all, we have to show those 4 conditions hold by this inner product. So we have to take 3 x, y, z. Usually we will take x, y, z in vector space V and constant in the field, scalars from the field. Now let us take f, g and h from the vector space. These are all functions, right? And constants, let the constant be some even k in R. First condition, what is the first condition? Inner product of f plus h comma g. What is this one? By the definition, this one is integral 0 to 1 f of t. Instead of f here, f plus h. Yeah, before that you all must know f plus h. You must know this one, f plus h of t. This is equal to f of t plus h of t. Okay, this is the addition of 2 functions. So f plus h instead of f, so we get f plus g of t into g of t dt. Sorry, it is h. Okay, here it is h only, right? But this f plus h of t is equal to this one. So this can be written as integral 0 to 1 f of t g of t dt plus integral 0 to 1 h of t g of t dt. You all know, right? This integration can be splitted. Okay, so what is this one? This is equal to inner product of f comma g. This is inner product of h comma g. So we have shown the first condition. Inner product of f plus h comma g is equal to this one. This first condition is hold. Now we have to show the second condition. What is the second condition? Inner product of CF comma G. This is equal to integral 0 to 1 C times f of t into g of t dt. C is just a constant, a real number, so it can be simply taken outside into g of t dt. So this is equal to C times inner product of f comma g. So the second condition also holds. Second condition is hold. Third condition. Actually, what is the third condition? All of you recall. What is the third condition? Inner product of x comma y, the whole bar is equal to inner product of y comma x. Suppose the field is a real number system, the field f is equal to r, then this bar does not play a role, right? Because 5 bar is equal to 5 only. If the field is a real number system, then both are same only. Inner product of x comma y will be equal to inner product of y comma x only. Okay, the third condition. What is the third condition? Inner product of f comma g, the whole bar. This is equal to integral 0 to 1 f of t g of t dt. Actually, it's a real valued function over the real interval. The whole bar, if you put the whole bar, it's same as it's a real number. Even if you take the complex conjugation for the real number, you will get the same real number only, right? So this is equal to inner product of f comma g. So the third condition also hold. Now we have to see the fourth condition. The fourth condition. The fourth condition here is somewhat non-trivial. Let us try to conclude somehow. Let f be a non-zero function on closed interval 0, 1, non-zero continuous function. Okay, and f belongs to this one. Okay. Now we have to show that inner product of f comma f is positive. What is this one? This one is integral 0 to 1 f of t into f of t dt. So this is equal to integral 0 to 1 f of t the whole square dt. Note that f is a continuous function. F of t the whole square is a continuous function. F is a function defined on this interval 0, 1. F is a non-zero function. So surely at some point f will not be 0. At some point f will not be 0. So f of t so at that point f square will be positive only. F is a continuous function. So near that point there must be a curve like this one. So if you integrate this one, you get f of t is a non-negative function. Here f of t the whole square is a non-negative function, and we are integrating over this interval 0, 1. So f is a non-zero function. So at some point f is not positive. So f is a non-zero function. So at some point f square is positive. So at that point the f square, the curve will be somewhat like this, and this is nothing but the area under f square up to the interval 0, 1. So anyway, if you integrate this one, we will get some positive area only, because below this one we will get some positive area. So this will be positive. It's a property of continuity. You try to realize this one through real analysis. If f is a continuous function and if f is non-zero only, this is possible. Or otherwise, if the continuity is lost, this is not true. I am not giving the entire correct proof, but somewhat it's a proof. It's an application of continuity. So this one together with this new inner product is an inner product space. Let us now see one more vector inner product space. Before that, a definition. Okay. Conjugate transpose or adjoint, both are same name, of a matrix A. A is an m by n matrix that is usually denoted as A star. A star. This is nothing but the I comma jth entry of A star is nothing but the j comma ith entry of A the whole bar, or otherwise the adjoint conjugate transpose of A, that is A star. That is A star is equal to A bar transpose. A bar transpose. That is, if A is equal to 1 plus I, 2 plus 3I, 4 plus I, 5 minus 2I, then what is A star? You have to take bar as well as transpose. If you take bar and transpose, if you take transpose, this main diagonal will not change, simply bar. And if you take a bar as well as transpose, this will interchange, and if you put bar, this will become 4 minus I, this is 2 minus 3I. So if A is equal to this matrix, then A star, this A star is called the conjugate transpose of A or adjoint of A. This A star is equal to this one. This A star is nothing but A bar transpose. Now let us see one more example of an inner product space over the matrices. Let V be the set of all n by n matrices with entries from the field F, from the real entries or complex entries. For the matrix n by n matrices, if we define the inner product as trace of B star A, then show that this definition makes this vector space as an inner product space. Show that this is an inner product space. So we have to show that this definition, ensures those four conditions. First of all, what is trace? Trace of a matrix. Trace means, for example, take a matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. Trace means sum of the main diagonal. That is the trace of the matrix. Trace of the matrix A is equal to always summation AII only. 1, 1, 2, 2, 3, 3 entry we have to add up. So summation AII. This is the trace. Okay. Now we shall prove it. The first condition is, before that, take three matrices A, B, C. C from the vector space are the three n by n matrices and a scalar. Let it be, instead of C, already we have used capital C. So instead of that scalar C, I am using K from the field F. What is the first condition we have to show? Inner product of A plus B comma C. We have to show that the addition in the first component can be splitted. But the definition here, it is given as this is equal to trace of the second star into the first one. So C star into A plus B. But it's a matrix multiplication. We know matrix multiplication is associative because it's a vector space. So this C star A plus C star B. Trace of this matrix plus that matrix can be equal to trace of this matrix plus trace of that matrix, right? So trace of, you understand and then have to write trace of C star B. This is equal to inner product of A comma C. This is inner product of B comma C. So we have proved the first condition. So the first condition is proved it. What is the second condition? Inner product of K times a matrix comma B. This constant, the first component, should be taken out. But by the definition, what is the definition is given? B star into KE. But K is just a number. Number can be taken out. Think how, why. So this is equal to K times inner product of A comma B. So the second condition also hold. Now we have to show the third condition. Inner product of A comma B, the whole bar. This is equal to trace of B star A, the whole bar. This is equal to trace of, this bar can be taken inside, right? It is already B bar transpose. B bar transpose, it is on E. Now this bar can be taken inside. So this bar. So this bar can get cancels. So we get, this is, before that just note the point. We know that trace of a matrix A as well as trace of A transpose, both are same because the main diagonal won't change if you take even the transpose. So trace of this matrix, let it be. So trace of this matrix as well as trace of B star A, the whole transpose, both are same only. The bar as it is, both are same only. Okay, trace of, so if we take a transpose, it becomes as A transpose into B star transpose, the whole bar. But what is B star? B star itself B bar transpose. So transpose times again transpose. If you take, we will get the same matrix, right? So this is equal to A transpose and B bar, and this bar again comes here. And if you take this bar inside, we get trace of A bar transpose into B. Trace of A bar transpose into B. So this one is trace of A star B. This is equal to inner product of B comma A. So we have shown that inner product of A comma B, the whole bar, is equal to inner product of B comma A. Now let us show the fourth condition. What is the fourth condition? If A is a non-zero matrix, then we have to show that inner product of A comma A is positive. A is a non-zero matrix, so surely some I comma jth entry is not equal to 0, or some k comma I. entry not equal to 0 only, right? Let A be a non-zero matrix. What is inner product of A comma A? By the definition, this is equal to trace of A star A. Instead of B here we have got A, so A star. Trace of A star A. Trace of A star A. What is trace? Trace is a summation. I varies from 1 to n. 1 to n. A star A I comma I. The I comma ith entry of this matrix, where I runs from 1 to n. This is a trace, right? We are summing over all the terms in the main diagonal of this matrix, I comma I. Summation I varies from 1 to n, this one. The I comma ith entry of this matrix. I take a matrix here, another matrix. If we product, we will get a matrix I comma I entry. If we need I comma I entry, we have to take here ith row, here ith column. Here we have to multiple the corresponding terms. Here the column changes, here the row changes. So if we multiple this one, we get summation. From this matrix A star, we have to pick ith row, and the column has to change in the matrix A star. In the matrix A, we have to pick the ith column. Here row has to change, and where k runs from 1 to n. So we get this one. So this is equal to summation I varies from 1 to n and summation k varies from 1 to n. What is star? It's a bar transpose. If you take transpose, we get, instead of k I comma k, we get k comma I. So simply bar remains. See, Z is Z bar. Z is Z bar. So we get mod square. Summation I varies from 1 to n. Summation k varies from 1 to n. Mod aki the whole square. A is we have seen it is, we have taken that A is a non-zero matrix. So at least one of the entries of A will be non-zero. Hence the square also will be non-zero, and all other terms will be non-negative. So this is always positive because it's a non-zero matrix. One of the entries must be positive, must be non-zero, so its square must be positive. So we have proved that this is also positive for the non-zero matrix. So the set of all n by n matrices with the entries from the field F, together this inner product is called an inner product space. And this inner product, which inner product? The trace of B star A. This inner product is called Frobenius inner product. This inner product is called Frobenius inner product.